Okay, so for this video, I'm going to be going over the momentum test review problems from the class kick in terms of how to solve them. So we'll start here with Rex and Tex. So this is going to be a collision problem where we're going to want to use the conservation of momentum. So we see here Rex and Tex, they're in bumper cars, and Rex moves at full speed, 2 meters per second, and he rear ends Tex, who's at rest in his path. Tex and his 125 kilogram car lunge forward at 1.2 meters per second. Determine the post-collision speed of Rex and his 125 kilogram car. So I think a good way to start this problem is we know that we have to use the conservation of momentum. And we know that momentum is simply mass times velocity, right? So I have two objects here, m1 v1 naught plus m2 v2 naught. These are the initial momenta of Rex and Tex before the collision, and that has to equal the final momentum after the collision. So v1f plus m2 v2f. Now, some important things to note for this particular problem is that Rex and Tex have their individual mass, and they're resting inside of a cart that has a mass of 125. So for this one, you have to make sure you add the mass of the cart to the mass of Rex and Tex, right? So Rex is sitting inside a car with a mass of 125, and he personally has a mass of 84.5. Another thing that's important to note is that Tex is at rest, right? So Tex was at rest at the beginning of the collision, and Rex was the one that bumped into Tex. So going into here, I'm just going to write out what all the variables are. And then we can just fill in the values into the equation and solve for the unknown. The unknown being the post-collision speed of Rex in his 125 kilogram car. So we'll take Rex to be M1 and Tex to be M2. So M1 is going to be Rex and his car, right? So it's 84.5 kilograms plus the 125 kilograms of the bumper car, right? And that comes out to let's see here, 209, so 209.5 kilograms. And then M2 is going to be Tex, who's slightly more massive, but is still riding in the same 125 kilogram cart. And that comes out to, let's see, 216.4. We know that the initial velocity of Rex is going to be 2 meters per second. The initial velocity of Tex is 0. The final velocity of Rex, that's what we need to find, right? We need to find the final velocity of Rex. And then the final velocity for Tex, it says in the problem, 1.2. All right. So I've noticed it's a lot easier for students to just start putting the values into the equation. You can solve for it straight up, right? Just solving for v1f by doing the algebra. So you move m2 v2f over to the other side and divide everything by m1. But let's just plug in the values and calculate them independently, so we're less likely to make a mistake. So here we have m1 is 209.5. So we have 209.5 kilograms times v1 naught, which is 2 meters per second. The initial velocity of Tex is 0, so I can just make that 0. All right, so his initial momentum is 0. And then that has to equal the final momentum of the system. So we have Rex here, M1 is 209.5 kilograms times V1F plus the momentum of Tex after the collision. So it's 216.4 kilograms times V2F, right? So V2F is going to be equal to 1.2. I'm writing a little small because I'm running out of space here. But let's perform all the calculations. All right, so 209.5 times 2, that comes out to 409. Wait, no, that comes out to 419. Yeah, 419. Okay, so we have 419 kilogram meter per second. All right, and then plus 0, well, that's just 0. And then here we have 209.5 kilograms times V1F plus the final momentum of Tex. So it's 216.4 times 1.2. Let me put that in my calculator and we'll go through it. All right, so doing that calculation, we have 216.4 times 1.2. We get 259.68. I'll just call it 259.7. Okay. So this is the final momentum of Tex. And then we have the initial momentum of the system, which is just the momentum of Rex. So I know that whatever's left over has to be the final momentum that Rex is going to have. So Rex has all the momentum of the system at the beginning. He bumps into Tex, gives Tex some of his momentum, and we're determining what's left over, right? At the end of the day, we're trying to figure out his speed, but we're using the conservation momentum in order to do that. We're going to find Rex's remaining momentum after the collision and then divide that by the mass in order to get the final velocity for Rex. So what I'm going to do is I'm going to take this 259.7 and I'm going to move it over to the other side of the equation, right? So by subtracting both sides by 259.7. So here I have I'm going to subtract both sides by 259.7. Okay, and then I got 419. So 419 minus 259.7, and I end up with 159.3 kilogram meter per second. So that's basically the remaining momentum that Rex has to have in order for the conservation momentum to hold. So that is going to equal 209.5 kilograms times V1F. And then I would divide both sides by the mass of the Rex car system, right? Because Rex is sitting inside the car. That's 209.5. And we get, so divide that by 209.5. We get 0.76 meters per second. Yep. All right, so divide both sides by 209.5. And then we get a final velocity for Rex equal to 0.76 meters per second. And that's how you solve that one. So now the very next problem. Now we have a sports car, and it's moving at 14.5 meters per second when it rear ends a stopped car that has an identical mass and is at a stoplight. The two cars entangle and move together after the collision. What is their speed immediately after the collision? So with this one, what's interesting is you don't even need to know what the mass of the sports car is. So let me explain. Here we have a perfectly inelastic collision where the two cars are going to stick together, right? So here we have M1, we have M2. We know that they have to equal each other, right? Because it says so in the problem. So M1 is equal to M2, right? So they have identical masses. V2 naught here is equal to 0, and then V1 naught is equal to 14.5 meters per second, right? So M1 is traveling towards M2. After the collision, they're going to stick together. Okay, so they're going to stick together after the collision. That's how you know it's a perfectly inelastic collision. And they're going to move as one unit, right? So this is like the big fish, little fish problem, where they're going to be moving together with some new final velocity. And we know that final velocity is going to be less than the initial velocity. I'm going to make this vector a little bit bigger, representing the velocity. So this is the initial velocity of the car, V1 naught, and this is the final velocity of the system, which is clearly going to be less. Now, if you actually write out the equation, right, so for them sticking together, I'm just going to write out the conservation of momentum. The one thing that you need to think about is the fact they stick together, that means they're traveling with the same final velocity. So the way that I can write the final momentum of the system is I basically treat it like one large object, right, with a total mass of M1 plus M2. We can simplify this even further. So we know that the initial momentum of the car at the stoplight has to be 0 because it's not moving, right? So you have 0 initial velocity. Anything times 0 has to equal 0. And then we also know that these two masses are the same. So I'm just going to write it as just 2 times m1, right? So you'll see what I mean. So I have m1 v1 naught plus 0 equals m1 plus m2, but we know they're the same, right? So we know that m1 is equal to m2. So I have 2 times m1 times vf. And then if I rearrange this equation, I can divide both sides by 2m1, right? And, well, we know the m1s are in both terms, so they cancel out. Basically here we have that vf has to equal v1 naught divided by 2. That's it. So you could plug in the numbers if you want, right? So they tell you the mass of the sports car is 989, and it crashes into an identical car that has the same mass of 989. You know, you can also just reason that, well, if I have these two objects with the same mass, one of them is not moving, and then they stick together after the collision, I know the final velocity has to be half as much, right? So basically it's as if the system doubled its mass for the same momentum by a conservation of momentum. So here we have, if it has a velocity of 14.5, right? Well, it's just 14.5 meters per second divided by 2, and we end up with 7.75 meters per second. Wait, what am I doing? That's not 7.75. That is 7.25 meters per second. All right, and that's how you solve that one. So not too bad. Now, next one, let's look at the next problem. All right, so now these ones are a bit more involved because there's multiple steps. So what we need to do is we need to figure out first the change in velocity of the ball. So here we have a volleyball game. Josie makes a clutch play. The 0.276 kilogram volleyball is moving at 6.07 meters per second. She lunges and bumps the ball in the opposite direction at 3.74 meters per second, or 64 meters per second, just before it strikes the ground. So you got to calculate the change in velocity of the ball. Magnitude only, no plus or minus signs. So that doesn't mean that you ignore the fact that they're going in opposite directions, right? So the ball is initially going towards the ground, and then she bumps it with her fist, and then it's going to be moving upward. But you still just, it's only asking for the magnitude, so you can just put the actual value, right? It doesn't matter what you call positive or negative. But the fact that they are going in opposite directions, right? The ball's initially going towards the ground, and then it's bouncing up and away from the ground. That affects what the change in velocity is going to be, right? So I'm going to draw them out as vectors. So we're just going to say that we have this volleyball here, and it's moving down with a velocity of 6.07 meters per second. And then after the collision, Josie makes her clutch play, and now the ball is moving upwards with a velocity of 3.64 meters per second. Now, for the sake of the problem, I'm just going to call up positive and down negative so we can see what the change in velocity is. This is the initial velocity of the ball. This is the final velocity of the ball. We're trying to figure out what the change in velocity is. So we have VF minus V naught. That's what the delta means for the change in velocity. So if I call up positive, I know VF is going to be positive 3.64 meters per second. And I have to subtract from that the initial velocity. So it's going downward with a velocity of 6.07. I'm going to be calling down negative. So it's minus negative 6.07 meters per second. And then when you do the math, you end up with 9.71 meters per second. So that's what the change in velocity is, 9.71. And I think an easy way to think about bouncing is, so why is the change of momentum, or I'm sorry, not change of momentum, but the change of velocity so large? One way to think about it is there's like two parts. So there's one part where during the first part of the motion, the ball is going from 6.07 meters per second to 0, right? So the ball's moving downward, and it has to slow down to a velocity of 0 before it begins to move upward, right? So that initial part is a change of 6.07, and then it has to move, it has to have an additional change of velocity of 3.64. So when you think about it that way, you understand that the total change in velocity is actually 9.71. But it's basically, you just look at the vectors, right? So we know initially it's going down, then it's going up, and you just use the equation. So we have 9.71 meters per second. We need to find the change in momentum of the ball. Well, this is pretty easy. We know that momentum, P, is equal to mass times velocity. So the change in momentum, well, that's just going to be the mass times the change in velocity, right? The mass of the volleyball, it doesn't change. It's constant. So all I'm going to do is I'm going to take this 9.71, that's the change in velocity. I'm going to multiply it by the mass of the ball. So we see here in the problem, the mass of the ball is 0.276. All right, so my change of momentum is 0.276 kilograms times 9.71 meters per second. And this gives us a momentum. Let me calculate this real quick. I end up with about 2.68 kilogram meter per second. So that is the change in momentum of the ball. Okay, and here we have, we need to now figure out what the average force is. So the average force Josie applied to the ball if her forearms were in contact with it for only 0.0416 seconds. Magnitude only, no plus or minus sign. So here, what we need to do is we have to use the impulse momentum theorem, right? So the impulse momentum theorem states that the impulse has to equal the change in momentum. Okay, and the impulse is defined as the force times the impact time, right? So her forearms were in contact with the ball for 0.0416 seconds, and we're trying to calculate what that average force was. So here I have the force times the impact time. That has to equal the change in momentum. Okay, so here we know the change in momentum is 2.68, and the impact force, we need to solve for that. So we're going to divide both sides by the impact time, right? So, and then now we can just plug in the values. So we have 2.68 kilogram meter per second. And we're going to divide that by the impact time of 0.0416 seconds. And then we end up with an average force of about 64.4 newtons. Okay. Now, for the very last problem, this is going to be a graph. So you're going to be given an impulse graph, and you have to be able to read the impulse graph in order to get key information from the problem. Whether or not it's the total change of momentum or how much the speed changes. This is similar to that one problem that we had for the impulse class kick, right? So that one graph problem that students tend to struggle with, there is going to be one like that on the test. So let's go over this one. Here we have an object with a mass of 2 kilos. It experiences a force in newtons according to the force versus time graph shown, and we have the time interval from 0 to 5 seconds. We need to figure out what is the total change of momentum of the object. Well, from the previous problem, we know that the total change of momentum has to equal the impulse, because that's the impulse momentum theorem. And we see here for a force versus time graph, the area is going to equal the impulse, right? The reason for that, I mean, if you think about it, when you take the area of a graph, right, it's as if you're taking the variable in the vertical axis times the variable in the horizontal axis, right? That's how you calculate an area. So we're going to have force times time, and we know from the previous problem, and just in general, impulse is equal to force times time. So when you have a force versus time graph, if you take the area of the graph, you're going to be getting the impulse imparted on the object. So we're looking at the total change of momentum, so we have to do it from t equals 0 all the way to t equals 5. Notice here that the graph is already kind of split up into 3 different chunks. So we're going to calculate the area of those 3 chunks, and we're going to add them all up. So for the first 2 seconds, we see that the force is linearly increasing from 0 newtons all the way up to 10 newtons. And we need to find the area of that first chunk. So we have a height of 10, we have a base of 2, and this is a triangle, right? So the area of a triangle is 1/2 base times height. So 1/2 of 2 times 10, well, that just comes out to 10. I'm going to use the units Newton seconds for impulse, well, because force is measured in newtons and time is measured in seconds. But just know it's the same exact thing as kilogram meter per second, right? So the units of impulse in terms of Newton seconds, That's the same thing as a kilogram meter per second, which is a unit for momentum, right? You can use either or, right? If you want to put 10 kilogram meter per second, that's fine. So we have 10 Newton seconds for the first 2 seconds of the trip. Now for the middle part here, well, it's just a rectangle. So we just take the base times height. We have a base of 2 and a height of 10. So we have 20 Newton seconds of impulse here. And then the very final part, we have this triangle with a base of 1, a height of 10, but you multiply by 1/2, right, since it's a triangle. So 1/2 times 1 times 10, that comes out to 5 Newton seconds. And if you add all of these up, we have 10 plus 20 plus 5. We have a total impulse of 25 Newton seconds, right? I can also write it out. So 10 plus 20. Wait, what am I doing? Not 25, 35. Right, 10 plus 20 is 30, plus another 5, we get 35. All right, so 35 Newton seconds. All right, I'm a little tired messing up the calculations. But here, what is the change in speed from t equals 1 to t equals 2? So for this, you need a little bit more information. So we need to know the mass of the object. That's stated in the problem as 2 kilograms. The reason why is basically we just calculate what the total change in momentum is, right? What we need to find is the change in momentum from t equals 1 to t equals 2 seconds, and then we're going to use that in order to figure out what the change in speed is, right? So let me go over the whole process. So first things first, we need to figure out what the change in momentum is from t equals 1 to t equals 2. So I'm actually going to, here, I'll do it here on the graph. So here, I'm going to erase this a little bit here. Right, so we already know that's 10 Newton seconds. And now what I'm looking for is this area right here. So this area here from t equals 1 to t equals 2, we need to figure out what that area is. So that's a trapezoid. Me personally, the way I think of it is, well, if I'm going from 0 to 10, right, if the force is linearly increasing from 0 to 10, I know that the force here has to be 5 newtons, right? So I'm going from 5 newtons to 10 newtons from t equals 1 to t equals 2. Actually, it might be kind of easier to see it like this. So what I'm going to do is I'm just going to split this up into 2 parts. So I have here this triangle up here, right, which is going to have an area equal to 1/2 base times height, because that part's a little triangle. So we have a base of 1, a height of 5, times 1/2. So it's 2.5 Newton seconds. And then this area, let me use a different color. This area over here is just a rectangle, right? So it has a height of 5, a base of 1. And multiply that together, we get 5 Newton seconds. All right, so here we know that the impulse, right? So the impulse from t equals 1 to t equals 2 is equal to 7.5 Newton seconds. All right. We also know that has to equal the change in momentum, because that's what the impulse momentum theorem is, that the impulse imparted on an object, the force, average force times the impact time, that has to equal the change in momentum. And we know that the change in momentum, another way to write it, is m delta v. And notice this problem is just asking about the change in speed. So we need that delta v. We know delta p has to equal 7.5. We know the mass is equal to 2 kilograms. So another way to write this is delta v is equal to delta p divided by m. Delta p has to equal 7.5 Newton seconds. And we're going to divide that by the mass of the object, which is 2 kilograms. And we end up with a change in velocity of 3.75 meters per second. So you solve that one. So basically, you're using the impulse graph to get information about the change in velocity, and that just requires one extra step. We know the impulse can equal the change in momentum, and if you divide the change in momentum by the mass, that gives you the change in velocity, or change in speed in this case, which is very similar to the problem we did on the impulse class kick. You had to find I think it was Calvin and Hobbes on a sled. You had to find the change in velocity at different points. So part C, the objects, if the object were to start from rest, what would its velocity be after the first 4 seconds? So basically we're doing the same thing. We're finding what the change in velocity is, and we know that, you know, its initial velocity is going to be 0, and we're going to be doing it for the first 4 seconds. So, well, for the sake of simplicity, I'm just going to erase what I have here so we can look at the next scenario. All right. So now we need to look at the speed at t equals 4, right? So after the first 4 seconds of motion, we need to figure out what its speed is. So now we're figuring out this whole area here. I'm going to be doing it from scratch just so you get used to the process. So, well, from previously, we know this area here for this triangle is going to be equal to 10 Newton seconds, right? Because 1/2 base times height. This area here is 20 Newton seconds. So we have a total of 30 for the first 4 seconds, right? So the impulse from t equals 0 to t equals 4, we have 30 Newton seconds of impulse. And we know the object starts from rest, right? So V naught is going to be 0. We're going to do the same process that we did in the previous problem. So we know that's going to equal the change of momentum, which is equal to m delta V. So let's solve for delta V, right? We're going to take the change of momentum divided by the mass. So we have a change of momentum of 30 Newton seconds divided by the mass of 2 kilograms. And we end up with a change in velocity equal to 15 meters per second. And if you think about the change in velocity equation, right, so we have VF minus V naught. Well, if V naught's 0, right, because he starts from rest, well, then we know the change in velocity has to equal the final velocity, right? So I start from rest, I have a change of velocity of 15. Well, that's what my final velocity is, right? So we have a final velocity of 15 meters per second. And finally here, it says, what is the momentum of the object at t equals 3 seconds if the object started from rest? So it's kind of like the previous problem, except working backwards, we're going to be just figuring out what the moment. Actually, you don't have to work backwards. You don't have to worry about the using the momentum equation, because all you're going to do is find the impulse. So now we got to find the momentum of the object at t equals 3 if the object started from rest. So again, it starts from rest. V naught is 0. Right, we know the initial momentum is 0. We're going to look at the graph to see how much impulse the object encounters during the first 3 seconds, right? So I'm going to erase all this again, just so you can see the process from scratch. All right, so we know for the first 3 seconds, it's this area here. Actually, I'm going to use a different color. So it's this area here, this whole bounded region. And this part over here, just like last time, we know it has to have an area of 10 Newton seconds. All right, and then this region over here, I'll just use the same color. This region over here, from t equals 2 to t equals 3, that's just a base of 1 second, and that has a height of 10 newtons. So this is another 10 Newton seconds of impulse. So my total impulse so the impulse from t equals 0 to t equals 3, that equals 20 Newton seconds. All right, and that has to equal the change of momentum. We know the initial momentum has to be 0, right? So if the initial momentum is 0, right, so change of momentum is PF minus P naught. Well, this has to be 0. So basically, it starts from rest, it has 0 momentum, there's 20 Newton seconds of impulse imparted upon the object, so we know that the final momentum has to equal that change of momentum, right? I'm actually just going to write it as kilogram meter per second. Again, those are the same units, so Newton seconds or kilogram meter per second. Just by convention, when you're talking about momentum, you typically use kilogram meter per second, and when you're talking about impulse, you use Newton seconds. But they're both the same thing. If you were to write Newton seconds for momentum, that would be totally fine. All right, well, anyways, that's pretty much it. That's how you approach these problems, and you'll be doing them in class. So if you have any further questions, just let me know. But yeah, that's pretty much it.